March 7, 1945. 1,520 hours. The Rhine River, Remagen, Germany. Private First Class Vincent Castellano stood at the edge of the Ludendorff Bridge and looked down at water that was moving faster than any river had a right to move. The Rhine was swollen with spring melt, dark and churning, carrying debris and broken equipment from battles upstream. The bridge itself was a massive steel structure, over 1,000 feet long, designed to carry trains across one of the most important natural barriers in Europe. Right now, it was the only intact bridge across the Rhine for hundreds of miles, and both armies knew exactly what that meant. The Americans needed to get across before the Germans could destroy it. The Germans needed to destroy it before the Americans could get across. And Vincent Castellano, who had spent the last 15 years of his life installing toilets and fixing water heaters in Brooklyn, was about to become the only thing standing between success and disaster. Castellano wasn't a combat engineer. He wasn't a demolitions expert. He wasn't trained in bridge construction or structural analysis, or any of the specialized skills you'd expect from someone tasked with keeping a critical piece of infrastructure functional. He was a plumber. A good one, according to the customers who'd kept his small business afloat through the Depression, but still just a guy who understood pipes and pressure and how water moved through enclosed spaces. When he'd been drafted in 1943 at the age of 34, the Army had looked at his civilian occupation and assigned him to a combat engineer battalion with the assumption that someone who worked with pipes could probably figure out military engineering. It was the kind of logic that made sense to people who'd never actually done either job. For the past 18 months, Castellano had been attached to the 9th Armored Division, mostly doing basic maintenance work, occasionally helping to clear rubble or repair damaged infrastructure. Nothing in that experience had prepared him for what he was looking at right now. The Ludendorff Bridge had been built by the Germans during World War I, a dual-track railway bridge designed to move troops and supplies across the Rhine. It was a massive piece of engineering, steel trusses, stone towers, a roadway that could support the weight of locomotives. On March 7, 1945, as American forces pushed into Germany, a small unit from the 9th Armored Division had captured the bridge in a surprise attack before German engineers could destroy it. It was one of the most important Allied victories of the war. For the first time, there was a direct route across the Rhine, a way to pour troops and equipment into the German heartland without having to conduct a massive river crossing under fire. Eisenhower himself called it a stroke of fortune, but fortune only mattered if the bridge stayed standing long enough to be useful. The problem was that the Germans had tried to destroy it. During the American assault, German engineers had detonated demolition charges that had been pre-positioned on the bridge. The explosions had been massive, but they'd failed to bring the structure down completely. Instead, they'd damaged it severely, weakening critical support members, cracking load-bearing beams, and creating structural problems that were growing worse with every vehicle that crossed. Army engineers had been brought in to assess the damage. Their conclusion was unanimous. The bridge was unstable and getting worse. It needed immediate repairs, but those repairs required specialized equipment, trained personnel, and most importantly, time. Time to close the bridge to traffic while work was done. Time that the Allied command absolutely could not afford. Thousands of troops were waiting to cross. Every hour the bridge stayed open meant more divisions getting into Germany, more pressure on the Wehrmacht, more progress toward ending the war. The engineers were told to keep the bridge functional regardless of the risks. By March 10, 3 days after its capture, over 8,000 troops had crossed the Ludendorff Bridge. Supply trucks, tanks, artillery pieces, all rolling across a structure that was visibly sagging in places. Engineers had identified the most critical problem. One of the main support beams on the western side had been cracked by the German demolition attempt and was now slowly failing under the constant load of traffic. If that beam gave way completely, it could trigger a progressive collapse that would drop the entire bridge into the Rhine. They'd tried to reinforce it with timber supports, but timber wasn't strong enough for the loads involved. They'd tried to redistribute weight by restricting which lanes traffic could use, but that just slowed the flow of troops across without actually solving the structural problem. What they needed was a way to support that damaged beam, to take some of the load off it until proper repairs could be made. But the beam was in an awkward position, partially underwater, difficult to access, and subject to constant stress from the current of the Rhine. That's when Lieutenant Morrison, the engineering officer in charge of bridge maintenance, made a decision born of desperation. He'd been reviewing the personnel files of every man in the engineering battalion, looking for anyone with relevant experience. When he saw that Castellano had been a plumber in civilian life, something clicked. Plumbers worked with structural support systems. They understood how to brace pipes that carried heavy loads. They knew how to work in confined spaces, often underwater, often with improvised materials. It was a stretch, but Morrison was out of better options. He found Castellano on March 11th, working on a water supply line near the bridge approach. "Private, I need you to look at something." Castellano followed Morrison down to the riverbank, then out onto a small maintenance platform that had been built to allow access to the underside of the bridge. Morrison pointed at the cracked support beam. It was a massive piece of steel, maybe 3 feet across, running diagonally from the bridge deck down to a stone pier that sat partially in the water. The crack was visible even to Castellano's untrained eye, a dark line running through the metal, probably 6 inches wide, with smaller fractures spreading out from it like a spider web. "That beam is holding up about 200 tons of bridge deck," Morrison said. "If it fails completely, we lose the bridge. The engineers say we need to take the bridge offline for at least 48 hours to do proper repairs. Command says that's not acceptable. We need to keep traffic moving." He looked at Castellano. "You're a plumber. You understand structural support. Can you think of anything we can do?" Castellano stared at the beam. This was so far outside his area of expertise that it was almost funny. He fixed leaking faucets. He installed water heaters. He cleared clogged drains. He didn't repair bridge beams that were holding up hundreds of tons of steel while a river tried to knock them down. But Morrison was looking at him with the kind of desperate hope that Castellano had seen before on the faces of customers who had a burst pipe flooding their basement and no money to pay for proper repairs. The look that said, "I know this isn't your job, but you're the only one here who might have an idea." And despite himself, despite the absurdity of the situation, Castellano found himself thinking about the problem the way he'd think about any structural support issue. The beam was cracked but not completely severed. It was still carrying load, but that load was making the crack worse. Every vehicle that crossed the bridge added stress. Every hour that passed, the crack propagated a little further. Eventually, probably soon, the beam would fail catastrophically. The solution wasn't to fix the beam itself. That would require welding equipment, specialized steel, and conditions that didn't exist in the middle of a combat zone with traffic constantly rolling overhead. The solution was to take load off the beam, to provide an alternative support structure that could carry some of the weight. In plumbing terms, it was like adding a support bracket to a pipe that was starting to sag. You didn't repair the pipe itself, you just stopped it from getting worse. Morrison looked confused. "Pipe? For what?" Castellano pointed at the beam. "I can't fix the crack, but I can brace it. If I run a pipe from the pier up to the beam above the crack point, angled correctly, it'll create a support structure that takes some of the load off the damaged section. It's the same principle as a buttress on a building. You're just adding support where the structure is weak." Morrison was already shaking his head. "We don't have that kind of pipe. We don't have anything close to that." Castellano felt the idea slipping away. Of course they didn't have pipe. Why would they? This was a military operation, not a construction site. Then Morrison paused. "Wait. There's a damaged German bunker about half a mile from here. The engineers were going through it yesterday, checking for booby traps. It had some kind of ventilation system, large metal ducts running through it. Might be what you're looking for." They found the bunker 30 minutes later. It had been hit by artillery, the roof partially collapsed, but the ventilation system was intact. Massive steel ducts, maybe 10 inches in diameter, running through the underground structure to provide air circulation. They were better than pipe, thicker walls, stronger construction, designed to handle structural load as part of the bunker's framework. Castellano measured them. 25 feet long, perfect diameter, and most importantly, they could be cut free and transported. The only problem was that this was a ventilation duct from a German military installation, and Castellano was proposing to use it to repair an American bridge. There were probably regulations against that. Probably a lot of regulations. Morrison looked at the duct, looked at Castellano and said, "Get it out. I'll worry about the paperwork later." It took 4 men and a truck to extract the duct and transport it back to the bridge. By the time they arrived, it was nearly 1800 hours, and traffic was still flowing across the bridge in a steady stream. Castellano studied the geometry, calculating angles in his head the way he'd calculate pipe runs in apartment buildings. The duct needed to run from the base of the pier up to the beam at about a 60-degree angle, positioned so it would provide maximum support at the point where the crack was worst. But installing it meant working partially in the water, in current that was strong enough to knock a man down, with traffic rumbling overhead causing constant vibration. And they'd need to do it without closing the bridge, because closing the bridge wasn't an option. Lieutenant Morrison gathered the engineering team and explained what Castellano wanted to do. The response was predictable. This wasn't proper engineering. This wasn't approved methodology. This wasn't how you repaired a bridge that was carrying the entire weight of the Allied advance into Germany. One of the sergeants pointed out that using a German ventilation duct as a structural support member violated about a dozen engineering standards. Another noted that even if it worked temporarily, it would need to be inspected and approved by qualified bridge engineers before it could be considered safe. Morrison listened to all of it, then said, "The bridge is going to fail in the next 24 to 48 hours if we don't do something. Command won't authorize closing it for repairs. Private Castellano has an idea that might work. Unless someone else has a better suggestion, we're doing it his way." No one had a better suggestion. They started work at 1900 hours, as the light was fading. Castellano waded into the Rhine with a team of 4 engineers, carrying rope and tools. The water was chest deep at the pier, the current strong enough that they had to brace themselves against the stone to avoid being swept downstream. They positioned the steel duct at the base of the pier, one end resting on the foundation, the other end angled up toward the bridge deck. The challenge was securing it. The duct needed to be firmly attached to both the pier and the beam, capable of handling enormous compressive force as it took load off the damaged section. Castellano worked by feel as much as by sight, his hands numb from the cold water, using techniques he'd learned installing support brackets for oversized pipes in building basements. They used salvaged cable to lash the base of the duct to the pier, wrapping it multiple times and tightening it until the metal bit into the stone. Then Castellano climbed up the makeshift brace, using the duct itself like a ladder, until he reached the point where it met the bridge beam. This was the critical connection. The top of the duct needed to press firmly against the beam above the crack, creating a load path that would bypass the damaged section. He used a combination of steel wedges and additional cable to secure it, hammering the wedges in place with a sledgehammer while traffic continued to rumble overhead. Every time a heavy vehicle crossed, the bridge shuddered, and Castellano felt the vibration through the duct. But the brace held. The geometry was working. The angled support was taking load off the cracked beam, redistributing it down through the duct to the solid foundation of the pier. They finished the installation at 2,130 hours. Castellano climbed down, exhausted, soaking wet, his hands bleeding from a dozen small cuts. Lieutenant Morrison inspected the work with a flashlight, checking the connections, testing the stability. The steel duct was now an integral part of the bridge structure, a diagonal brace running from water level up to the damaged beam, taking some of the crushing weight that had been threatening to tear the beam apart. It looked improvised because it was improvised. It looked temporary because it was temporary. But it was also functional. Morrison ordered stress measurements taken on the damaged beam. Within an hour, engineers reported that the crack had stopped propagating. The load on that section of the beam had decreased by approximately 30%. The improvised brace was working. Word spread quickly through the engineering battalion. The plumber from Brooklyn had braced a bridge with a German drainpipe. It sounded like a joke. It should have been a joke. But the numbers didn't lie. The Ludendorff Bridge, which had been on the verge of catastrophic failure, was now stable enough to continue carrying traffic. Not indefinitely. The brace was a temporary measure, and proper repairs would still be needed eventually. But it bought time. Days, maybe a week, for thousands more troops to cross into Germany. Lieutenant Morrison filed a report describing the repair in technical language that made it sound more official than it was. He didn't mention that the support structure was a ventilation duct from an enemy bunker. He didn't mention that it had been installed by a plumber with no bridge engineering experience. He just noted that an improvised structural support member had been successfully implemented to stabilize a damaged load-bearing component. The bridge stayed open. On March 12th, another 6,000 troops crossed. On March 13th, the first tanks from Patton's Third Army rumbled across, heading deeper into Germany. The improvised brace held. Engineers monitored it constantly, checking for signs of failure, ready to close the bridge if anything started to give way. But the drain pipe that Castellano had installed did exactly what he'd calculated it would do. It took load off the damaged beam. It redistributed forces through solid geometry. It kept a critical piece of infrastructure functional during one of the most important operations of the war. And it did all of this while violating every regulation about proper bridge maintenance that had ever been written. On March 17th, 10 days after its capture, the Ludendorff Bridge finally collapsed. Not because of Castellano's brace failing, but because the cumulative damage from the German demolition attempt, combined with 10 days of heavy traffic and inadequate repairs, finally overwhelmed the structure. The bridge fell into the Rhine at 1,500 hours, killing 28 American engineers who were working on it at the time. But by then, over 25,000 troops had crossed. Pontoon bridges had been constructed nearby. The Rhine was no longer an obstacle. The strategic value of capturing the bridge intact had already been realized, and Castellano's improvised repair had contributed to that success by keeping the bridge open for 6 additional days beyond what engineering assessments had predicted. There was no investigation into the unauthorized use of German materials for bridge repair. There was no court-martial for violating engineering standards. There was no official recognition of what Castellano had done. The collapse of the bridge dominated all the after-action reports, with focus on the engineers who died and the lessons learned about bridge maintenance under combat conditions. Castellano's name appeared in one paragraph of Lieutenant Morrison's final report, noting that PFC Vincent Castellano had demonstrated initiative in implementing field repairs to damaged infrastructure. That was it. No details. No explanation of how a plumber, with no formal engineering training, had solved a problem that trained bridge engineers couldn't figure out. Just a brief acknowledgement buried in paperwork that almost no one would ever read. Castellano survived the rest of the war. He was present at the final German surrender in May 1945, still attached to the 9th Armored Division, still doing maintenance work and occasional repairs. He came home to Brooklyn in November 1945 with a Bronze Star that cited meritorious service in support of combat operations, without specifying what that service had been. He reopened his plumbing business. The neighborhood had changed during the war, new families, new buildings, new problems that needed fixing. Castellano went back to installing water heaters and clearing drains, and doing the same work he'd done before the war, as if the previous 2 years had been some kind of strange interruption in a life that was always meant to be about pipes and pressure and making sure water went where it was supposed to go. He never talked about the bridge. When customers asked about his war service, he said he'd been with an engineering unit in Europe. That was true. That was enough. There was no point trying to explain to someone how he'd braced a bridge with a drain pipe, or why that had mattered, or how many lives might have been saved because the bridge stayed open for a few extra days. People didn't want complicated stories. They wanted to thank him for his service and then get their toilets fixed. Castellano understood that. He'd never been comfortable with attention anyway. He'd become a plumber because he liked working with his hands, liked solving practical problems, liked the satisfaction of making things work. The war hadn't changed that. If anything, it had just confirmed what he'd always believed, that most problems had practical solutions if you understood the principles involved and weren't afraid to use whatever materials you had available. In 1952, the Army published an updated field manual for combat engineers. It included a section on expedient bridge repairs under combat conditions that described techniques for temporary structural reinforcement using non-standard materials. The section included diagrams showing how angled braces could be used to support damaged load-bearing members, how load could be redistributed through improvised support structures, and how field repairs could extend the functional life of damaged infrastructure. The techniques were presented as standard engineering practice, with no mention of where they'd come from or who'd first demonstrated them. But buried in the technical language and official diagrams was the basic principle that Vincent Castellano had applied on a cold March evening in 1945, that sometimes the solution to an engineering problem wasn't better materials or more time or following proper procedure, but just understanding how forces worked and using whatever you had to make those forces go where you needed them to go. Castellano ran his plumbing business for 38 years. He hired his son in 1960, taught him the trade the same way his own father had taught him, by showing him how things worked, by explaining principles instead of just memorizing steps, by emphasizing that understanding was more important than equipment. The business grew slowly but steadily. By the 1970s, Castellano and Son Plumbing had built a reputation for being able to fix problems that other plumbers couldn't handle, for finding solutions when standard approaches didn't work, for understanding the principles well enough to improvise when necessary. Vincent Castellano retired in 1983 at the age of 74. He spent his remaining years in a small house in Bay Ridge, gardening and reading and occasionally consulting on complex plumbing problems that his son would bring to him. He died in 1991 at the age of 82. His obituary in the local paper mentioned his plumbing business and his war service, but provided no details about either. Here's what the obituary didn't say, what no official record properly captured, what exists only in scattered engineering reports and the fading memories of men who were there. The Ludendorff Bridge stayed functional for 6 days longer than engineering assessments predicted it would. During those 6 days, approximately 15,000 additional troops crossed into Germany. Those troops participated in operations that shortened the war, that saved lives on both sides by bringing the conflict to a faster conclusion. You can't draw a direct line from Castellano's improvised brace to any specific military victory, or calculate exactly how many lives were saved because the bridge stayed open. But you can look at the numbers and understand that his solution, implemented in a few hours with scavenged materials and practical knowledge, contributed to one of the most important Allied successes of 1945. The broader lesson extends beyond one bridge and one plumber. Military organizations, like all large institutions, tend to value credentials over competence, proper procedure over practical solutions, official approval over actual results. They write detailed regulations about how things should be done, and then enforce those regulations, even when circumstances make them irrelevant. This is understandable. Regulations exist for good reasons, and most of the time following proper procedure leads to better outcomes than improvisation. But there are moments, usually moments of crisis, when the regulations become obstacles rather than guides, when proper procedure takes too long or requires resources that don't exist, when the gap between how things should work and how they actually need to work becomes too large to ignore. In those moments, the people who save the situation are usually not the ones with the most impressive credentials or the deepest knowledge of regulations. They're the people who understand principles well enough to apply them in novel ways, who can look at a problem and see past the official solutions to the fundamental issues involved, who have enough practical experience to know what will work even if it's not what they were trained to do. Vincent Castellano was a plumber who happened to understand structural support because plumbing involves structural support. That understanding, combined with a willingness to try something that wasn't in any engineering manual, kept a bridge standing when trained bridge engineers couldn't find an acceptable solution within the constraints they'd been given. The Army eventually acknowledged, in its oblique institutional way, that the Remagen bridge operation had revealed important lessons about field engineering and improvised repairs. But those lessons were absorbed into doctrine and technical manuals without any real credit given to the individual soldiers who demonstrated them under fire. That's how institutions work. They learn from experience, but they credit the system rather than the people who made the system work. It's cleaner that way. It's more orderly. It fits better with the narrative that success comes from proper training and following procedure rather from individual initiative and unauthorized improvisation. But the soldiers who were there knew the truth. The engineers who watched Castellano install a drainpipe brace on a damaged bridge beam knew that they were witnessing something that shouldn't work according to the regulations, but did work according to the physics. The troops who crossed that bridge in the days after the repair knew that someone had figured out how to keep them moving forward when the official engineering assessment said it was too dangerous. And Lieutenant Morrison, who'd authorized the unauthorized repair and filed reports that carefully avoided mentioning how unorthodox it had been, knew that he'd made the right decision, even if it was technically the wrong decision according to every regulation in the book. That knowledge spread quietly through the ranks. Not through official channels. There was never a training bulletin about the plumber who braced a bridge with a drainpipe. But soldiers talked to each other. They share stories about things that worked, about solutions that weren't in the manual, about the times when someone ignored procedure and saved lives. Those stories become part of the unofficial education that makes soldiers effective, the practical knowledge that exists alongside the official training. And somewhere in that unofficial knowledge, passed from one soldier to another in conversations that no historian ever recorded, was the story of Vincent Castellano and the lesson he'd demonstrated, that sometimes understanding principles mattered more than following procedure, that sometimes the solution was sitting right in front of you if you knew how to look at it differently. and that sometimes the most important military innovations came from people who weren't supposed to have the expertise to innovate. Vincent Castellano fixed a bridge with a drain pipe. That's what happened. Everything else, the thousands of troops who crossed safely, the operations those troops conducted, the contribution to ending the war, the eventual incorporation of improvised repair techniques into official doctrine, all of that was just the result of one man understanding that load needed to be redistributed and having the practical knowledge to figure out how to do it with the materials available. He wasn't trying to revolutionize military engineering. He wasn't trying to prove that regulations were wrong. He was just trying to solve a specific problem that needed solving right now, and he happened to have the background and the insight to see a solution that trained engineers had missed. There's no monument to Private First Class Vincent Castellano. There's no mention of him in the major histories of World War II. His contribution to one of the most important bridge operations of the war exists only in a single paragraph of an engineering report and the memories of men who are mostly gone now. But for 6 days in March 1945, a German ventilation duct installed by a Brooklyn plumber kept the Ludendorff Bridge functional long enough to matter. And that simple improvised brace, installed in a few hours with scavenged materials, represents something fundamental about how wars are actually won, not through perfect planning or superior technology or following proper procedure, but through individual soldiers who understand their craft well enough to improvise when the situation demands it, who care more about solving the problem than following the rules, and who are willing to try something unconventional when conventional solutions aren't working. That drain pipe saved lives. Probably hundreds of them, possibly thousands if you count the cascading effects of keeping the bridge open and getting troops across the Rhine earlier than would otherwise have been possible. But there's no way to quantify it precisely, no way to point to specific individuals and say they lived because Vincent Castellano knew how to brace a damaged beam. The evidence is scattered through after-action reports and casualty statistics, and the simple fact that the bridge stayed standing longer than it should have. And in the gap between what officially happened and what actually happened, in the space where improvised solutions don't fit neatly into approved procedures, the truth about innovation and heroism gets lost. Vincent Castellano was a plumber who understood structural support. The Army needed someone who understood structural support, even if they didn't realize it at the time. And for a few critical days in March 1945, that plumber's practical knowledge made the difference between success and failure at a strategically critical location. That's the real story. Not a tale of impossible heroism or dramatic rescue, but the quieter truth about how essential problems get solved by ordinary people with practical skills who are willing to ignore the regulations and do what needs to be done. The drain pipe held. The bridge stayed up. The troops kept moving. And somewhere in Brooklyn, years later, an old plumber fixed leaky faucets and cleared clogged drains and never mentioned that he'd once braced a bridge that helped win a war.